So okay, let me wrap up this particular set of calculation by telling you one more thing. So using this complex representation to represent real trigonometric functions, it works well most of the time. So for example, let's say you have these two functions. You have functions f and g. That it's some function of, let's say, time, and g is another function of time. And it could be f is equal to a cosine of omega t, g is equal to I don't know, b cosine of omega t. And you have the complex versions of those. You have the complex f, which would be a times e to the I omega t. And you have complex g, which is b times e to the I omega t. And most operations you can do, it works out the way you would imagine. So if you want to, so for example, here are some operations you can do. F plus g, f minus g, some scalar, c times f. All these, you can do the same thing here. You can calculate f plus g, f minus g, and some scalar c times f. But one thing that you are seeing me avoid doing is I'm not multiplying these two functions together. Because so when I've done all of this, the only thing that it takes for me to go back to this representation is I can take any one of this and simply apply the real, take the real part, and I'll be done. But when you're dealing with products, that's where things get a little bit complicated. Because if you do f times g, let me just do this quick demonstration. Let's say I did, let's say I do f times g here. So f times g gives me a times b, cosine squared omega t. Right? Nothing complicated. All right, let me do the same, and that's the real part, and that's all that. Let me just try calculating f times g. So if I do f complex times g complex, this is what I get. A times b, so far so good. And this is what I have. E to the I omega t times e to the I omega t. So e to the I omega t squared. Oh, I can simplify that. I know how to do complex, exponential algebra. So it's the e to the I 2 omega t. And when you take the real part of this, you get cosine of 2 omega t. Does that look anything like that? Yeah, so something has gone wrong, right? And it comes down to this fact. When you represent f as a1 plus ib1 and g as a2 plus ib2, any addition or subtraction you do, it doesn't mix real and the imaginary part. So real part is kept by themselves, imaginary part is kept by themselves. So you can just use that, and then when you separate the real part out again, then everything's fine. When you do, so this is actually the complex version. So what we want to represent with the f is just this. What we want to represent with the g is just this. But when you do f times g, that's when the real and the complex parts mix. Because a1 times a2, that is in my product. a1 times a2 is there, so that's fine. But I also have the imaginary part times imaginary part. Minus I b1, oh sorry, not minus. So I squared, which is minus b1 times b2. And it's the second term that causes issues when you are doing product. having said all that, there's one particular operation you do with real function that looks much, much simpler with complex exponential. We were actually doing this calculation before earlier. Where did I write it? I guess it's this one. It's a version of this one. This is a place where I had a function that's periodic, and I want you to take its time average. And I went through these, sophisticated formulas to get to a pretty simple answer, 1/2. And this is something that's proven in a math class that I want proof. So let's see. So this only works with a periodic function. If you have a periodic function of f as a function of time, and it takes this form of some constant times periodic cosine of omega t, and you can imagine doing let me call it this way. So some average of f squared. So the mathematical representation of that would be the 1 over t, what I wrote here, 1 over t, 0 to t, f of t squared dt, right? And in the complex representation, this can written in a much more simpler way. This can be this. It's the complex representation of this function. So the complex representation would be a times e to the I omega t. Multiply that with the complex conjugate divided by 2. Gives you the same result as what you would get by going through the calculus. So whenever your final intended result is that you want to take the function, square it, and then average it as a function of time, then you can use this to really simplify your calculation.